followed up by the tutorials on Laplace transformation. So firstly, let us review how do we find the step response of the series RLC circuits. I've gone through this in the question 3, right, of the previous tutorial. And here I just review the steps again. And first step is actually to find the initial values of the voltage across the capacitors and the current through the inductors. Okay, the reason for doing so is that we know that the current through the inductor cannot change suddenly, immediately after switching, right? And the voltage across the capacitor also cannot change suddenly, immediately after switching. So this become the initial values of your circuits, right? Namely, before switchings, you find the steady state values, and immediately after switching, they will not change suddenly. So the first thing that you need to do is to find these initial values, so as to solve your differential equation later on. And we can also find the steady state values easily because the inductor behaves like a short circuit at steady state under DC conditions, right? This is a step DC circuits. So the signals at steady state will always be constant. DC means constant. And as a result, right, di dt, I constant, then di dt is 0, so the voltage becomes 0, which means short circuits. At the same time, I is equal to C dV dt for capacitors, so voltage constant, right, means no change with respect to time. It means the current is 0. Okay, if current is 0, it means that actually this capacitor behaves like an open circuit. Okay, you can visualize this way. You close this switch, then you start charging up until, right, the potential difference is the same. Then you cannot charge up anymore. No more current can flow through it. And here we can see that the initial current, right, for series RLC is here the final steady state values of the RLC circuits is 0. Okay, as for the steady state values, right, of your voltage, okay, we call V infinity, means that you allow sufficient time for the circuits to reach steady states. Okay, this voltage will be equal to Vs because there's no current flowing through. Here, I equal to 0. If I is equal to 0, Ohm's law says that the voltage across the resistor is also 0, right? I times R is the voltage across. Current 0 multiplied by any resistance, you get 0. So the voltage across this capacitor at steady state is actually equal to this voltage over here. Now, we use these circuits to analyze the response because we have learned from week 1 and week 2 that even if you have a more complex circuits, you can always simplify it to this form, right? You can simplify it to this form by using, for example, Thevenin's theorem. Then this will be your RTH, this will be your VTH. Okay, for simpler circuits, you can just use source transformations to transform it to this form. So the whole idea is that if you have a complex circuits, right? If you have a complex circuits, convert it into this equivalent form. And in this equivalent form, we know the standard solutions as analyzed in the lecture notes. Okay, the standard solutions will depend on two parameters, alpha and omega 0, right? Alpha and omega 0. For series RLC, right, this one you have to remember it, but it can be derived, right? If you don't remember it, it can be derived, especially in Laplace domain. Later on, I will point it out to you in probably the next tutorial, right? It can be derived, but at this stage, take note that you have to remember this, or you derive the differential equation. Once you derive the differential equation, you can also write this down, right? Okay, alpha is equal to R over 2L for series RLC circuits. Okay, if you have a complex circuits and you simplify it to this form, then this will be your equivalent values. Okay, even the inductors and capacitors, sometimes it can also be simplified. You have learned how to simplify the series parallel combinations of inductor and capacitor. Okay, which means that I can simplify, right, most of the circuits into this form so as to get the standard solution. And omega 0 is 1 over square root LC, right? Again, LC could be the equivalent form. Okay, we calculate alpha and omega 0 because the solutions of a standard second order differential equations actually depends on the values of your alpha and omega 0. And last week I showed it to you, alpha represents damping to the system. If alpha is large, that means that it's over damped, right? There's too much damping. So you get a slow response. If alpha is small, you have an underdamped response, which means oscillations, right? So it's easy to remember. Underdamped, you get oscillation, so you get the sine and cosine, right? The other two, there's no oscillation, which means that they are all exponential terms. And overdamped means that you have two distinct roots. Okay, this means that when you calculate this S1 and S2, based on your characteristic equation, right, because you have real roots, so you get two distinct values. Okay, sometimes when alpha is equal omega 0, you can see if alpha is equal omega 0, this term equals 0, then S1 and S2 are the same, right? That is the third case, which is called critically damped. Right, here there's a T, right? Because they have two real equal roots, to differentiate them, right, we put A2 and A1T, for example. So they actually represent two of them, right? Combinations of two of them. And notice that all the parameters that you need in this V, except A1 and A2, can be obtained from omega 0 and alpha, and omega 0 and alpha can be obtained from your RLC value, right? For example, for the first case, alpha 1 and alpha 2 is just calculating this, right? That means that you calculate this. This one will be your alpha 1, and this one will be your alpha 2. Okay, and if these are equal, then you only have alpha, correct? Only have alpha. Okay, for the underdamped, you need to calculate one more thing, which is omega d. Omega d is actually omega 0 minus alpha square, right? Omega 0 minus alpha square, which means that once you have calculated omega 0 and alpha, you can also calculate omega d, then you just put it into here. Where alpha is directly obtained from the value over here. So basically, actually this steps are very tedious, but it's very standard, right? Standard in the sense that you first calculate alpha and omega 0, series RLC, use this, okay? And then check the values of alpha and omega 0, right? And under these three circumstances, you have three different solutions. All the parameters in the solutions, except A1 and A2, can be obtained from alpha and omega 0. Okay, the only thing that you cannot obtain is A1 and A2. Okay, A1 and A2 can be determined from the initial conditions, right? Okay, before that, the next step is that you have obtained the general solution because you have obtained the steady state values based on simple analysis by letting inductor become short, capacitor become open. So this is just an analysis of a network with resistor only. Under steady state conditions, your energy storage elements, right, is basically not there because inductor behaves like short, capacitor behaves like open. So you can get steady state values, and one of these values that you obtain here, right, you just put it into here, this or this or this. Then you get the general solutions, right, which consists of the steady state value and the transient. Now the transient will disappear, as you can see, negative e to the power of negative t. So as t goes to infinity, all this disappears, and you reach the steady state value. Okay, as I said, the only two unknowns that you need to get is this A1, A2. Other than that, everything can be obtained from alpha and omega 0. So two unknowns, you need two equations, therefore you use two initial conditions. Okay? So from step 1, we have the initial conditions, we get two of them. voltage, current. Then you relate to your solutions over here. You get two equations, you solve for the two unknowns. All right, so this is basically what we have done last week. Okay, the parallel RLC, right? That was series RLC. Parallel RLC is similar in the sense that the steps are quite similar, except that we are solving a different configuration, so you have the different differential equation, right? But we can still perform circuit analysis. If you forgot about those formula, just spend a few minutes to derive it. For example, for this parallel RLC, I'm interested in the current, so I use Kirchhoff current law. Inflow equal to outflow, right? Inflow is this source current, DC, and for parallel combination, all the voltage are the same, right? Remember, parallel voltage same, series same current. Okay, if the voltage are the same, then the voltage across the capacitor is also the voltage across the inductor, which is also the voltage across the resistor. Now, the current flowing through the resistor is just Ohm's law, V over R. Current through the inductor is what we want, so we put I there. Right? You want to solve for I, so no need to convert to voltage. Just put I there, and then current through the capacitor is I equal to C dV dt. Okay, we just leave it there. Now here, what we want is I, right? If you want V, you can see that then you convert I to V. But now we want is I, so we convert V to I, right? Convert V to I. As I said, the voltage are all the same, so therefore you look at I is here. Okay, I is the current flowing through the inductor, so V is equal to L di dt, right? V is equal to L di dt. This is the basic law which you need to remember by heart, like you remember Ohm's law. And after that, we can substitute this into here, correct? Then we convert voltage to current. So you get this one after substitute this into here. Now dV dt, you just differentiate this one more time. dV dt is equal to d square I dt square. Then you substitute into here, you get this one, and d square v dt square is this I, right? This I. So d square I dt square, right, is a second order, so you end up with a second order differential equation. Now, as I say, if you forgot, right, the how to calculate alpha and omega 0, okay, this is what you can do. Okay, actually, you can see that first you compare with this 2 alpha, right? This is omega 0. Okay, I've gone through with you why it's written in this form last week, right? Because there's a b square minus 4ac, so this is 2, and this represents the frequency. Okay, if there's no damping, frequency of the oscillation if there's no damping. Okay, then from here, basically you can write down these two. Right, or right, you remember this by heart after you understand how it was derived, right? Do not just simply remember things, but go through it, understand how it was derived. Then from there, we know that, right, this is how the formulas were derived, and we just use it. Okay, and basically, if you look at this and compare with the previous one, okay, the only difference is the alpha has changed. Omega 0 is the same, right? Take note, omega 0 square root 1 over LC is still the same if for parallel. Okay, that means that you only need to remember one more new thing. Alpha is equal to 1 over 2 RC, right? Now, like the solutions is also in a similar form, except now we are dealing with current, right? So we have the transients and the steady states, and therefore there are three types of solutions similarly for the transients, depending on the values of alpha and omega 0. So it's in the similar form. Okay, the steady states values can be calculated from here. If you look at these circuits, okay, at steady state, this will become short circuits, all right? This will become open circuits, open. no more there. Okay, and because this is short, this voltage will become 0. Okay, if the voltage across the resistor is 0, remember no current can flow through it, right? IR will be equal to 0. Okay, if you're not sure, just use Ohm's law to verify. V over R is I. V is 0, divide by any R, you get 0 volts. Correct? You get 0 amperes. Now, if no current flowing through here, then all the current, IS, all the source current will flow through here. So your I infinity, right, this current at steady state is actually IS, the source current. Okay, this is also called the Norton's current. That means that your steady state value is actually the Norton's current, right? Because you find Norton's current by shorting the load, right? In this case, the inductor is shorted because of its property, V is equal to L di dt. So we can put this steady state values here, which is actually the source currents of the equivalent circuits. And finally, we find A1, A2 by the two initial conditions, right? So the step is similar. Let us review it. Find the initial values of the voltage across the capacitor and the current through the inductors. This is obtained if there's a switch there. It means that you have to find the steady state values of the voltage across the capacitor and the current through the inductor before switching, right? Before switching, the steady state value before switching. Okay, immediately after switching, because this will not change, the voltage across the capacitor cannot change suddenly. I is equal to C dV dt. Current through the inductor cannot change suddenly, right? L di dt. Therefore, immediately after switching, this will become the initial conditions, right? And we can find the steady state values first of the circuits after switching. T greater than 0 is after switching. Okay, just now I've mentioned this is shorted. This is open at steady state. Therefore, since this is shorted, no current can flow through here. IR equal to 0. Therefore, all the current will flow through here, right? So your I infinity is actually your source current. Okay, is also your Norton's current if you use Thevenin's theorem or Norton's theorems. Okay. And this R can be your equivalent resistance or your RTH, but even L and C, right? Sometimes you can also simplify them. So in other words, we start from this one because we already know in week 1 and week 2 that we can simplify circuits using equivalence circuits such as Norton's equivalence. Even source transformations can be done easily, right? Source transformation can be done easily to put into this form. So the idea is that you put into this form so that you can get the standard solutions which was derived in the lectures. And the standard solution depends on the two values of alpha and omega 0, which can be obtained from all these RLC values or the equivalent values if you started with a more complex circuits. Now the only thing new, as I say, is that for parallel, alpha is 1 over 2 RC, right? Omega 0 is the same as your series RLC, which is square root of 1 over LC. So it's quite easy to remember after you practice it a few times. And the solutions of your general, the general solutions, right, will depend on the values of alpha and omega 0, the relative values. If alpha is large as compared to omega 0, then we have overdamped, right? If alpha is small as compared to omega 0, then we have underdamped, because alpha represents damping. Now, if alpha is equal to omega 0, then we have critically damped, right? Just nice. And the solutions is obtained by putting one of them into here, depending on the value of alpha and omega 0, and put the steady state value that you have calculated just now, right? Together with it, basically this is your IS. Okay? And finally, we still have two unknown, A1 and A2, which should be obtained from the two initial conditions, because to solve for two unknowns, you need two equations. One initial condition gives you one equation. Okay, let us run through this by using the last problems of the last tutorial, right? 4.4. Now, there's a switch here indicating t equal to 0. It means that before that, it was closed, right? At t equals 0, you open it. At t equals 0, you open it. Before that, it was closed. So let us look at the case before it was open, right? And use it to find the initial conditions, which is the first step. Now, firstly, before switching, O minus t equal to 0, you open. So O minus means before, right? Before the switch was open. And before the switch was open, if you allow sufficient time for the circuit to settle down, it reaches steady states, then we can find the current through the inductors and the voltage across the capacitor by just simply analyze the circuits, which is just resistor network, right? Why? Because for capacitor, it behaves like open circuit at steady state. For inductor, it behaves like short circuit at steady state. So look at the circuits on the right hand side. They are just resistor and independent source. Okay, which means that you can analyze like what you have learned in week 1 and week 2. So to find the steady state values, right, we need not solve the differential equation, right? But that only allows you to find the steady state values. So at steady state, right, this is a steady state before switching. Take note, before switching, we know that the voltage across the capacitor, which is also the voltage across the resistors and inductor, they are all equal to 0, right? They are all equal to 0. Now this means that the voltage across the capacitor is equal to 0, right? We are interested in the voltage across the capacitor, current through the inductor, because they cannot change suddenly. So now we have found that the voltage across the capacitor is 0 because, right, the inductor has shorted and forced it to become 0. Okay, next is to note that we need to find this current through this inductor. Okay, firstly, we note that because this is shorted, there's no potential difference between 5 ohms. Okay, always remember this is connected to ground, correct? So if this is shorted, this is also 0 volts. Okay, and these are the same nodes. So this is also 0 volts. And same thing over here, this is also 0 volts. So there's no potential difference between them. Current can only flow if you have a potential difference, right? Like water flow from higher ground to lower ground. So similarly, current must flow from a higher voltage to a lower voltage. If there's no potential difference, no voltage difference, then current will not flow. Now there's no current flowing through here, remember? So the 3 ampere, when come to this junction, none of them will flow through here because no potential difference. So all of them will flow through here, therefore this is 3 ampere. And when come to this junction, this is open. So current also cannot flow into the capacitor now, and therefore it will flow through here. Okay, come to this junctions, right? Notice that here there's 12 volts, this 0 volts. There's a potential difference now. This 12, this 0. So therefore the current flowing through this is basically 12 divided by 4, right? 12 divided by 4, which is 3 ampere. 12 volts divided by 4. Now 3 ampere meet and flow downwards. So this becomes 6 ampere, Kirchhoff current law. Inflow equal to outflow, right? Okay, which means that in the end, okay, this is what we get. This current is equal to 6 ampere because 3 ampere come from the right, 3 ampere come from the left, and they combine to become 6 ampere. Now these conditions are important. These are the voltage across the capacitor, current through the inductor before switching, right? Before switching. Now that will become our initial conditions after switching, because according to this circuit's law, we know that the voltage across the capacitor cannot change suddenly, right? Current through the inductor cannot change suddenly. Otherwise, you have infinite values here, okay, which is not possible. Physical systems cannot go to infinite, right? It has to be finite, and this set some constraints on these changes. Okay, basically it's continuity in the sense that it has to be continuous. Okay, it cannot jump. Okay, let us look at the circuits after switching t greater than 0. Right? Sometimes we call O plus. Right? After switching is open, disconnected from this guy, okay, which means that you only left with this one. Right? Only left with this one, and look at it, it's just series parallel RLC. Now, if you have more complex circuits, right, sometimes maybe other circuits, just try to simplify to this form. Right? Try to simplify to this form by using what you have learned in week 1 and week 2. Right? Typically, source transformations, if is simple, more complex, you use Thevenin's equivalent. Okay, immediately after switching, we know that the voltage immediately after switching, O plus, have to be equal to the voltage before switching, just before switching, okay, because voltage of a capacitor cannot change suddenly. Now the current through the inductor also cannot change suddenly, so immediately after switching, it has to start from 6 ampere, which was the steady state value before switching, right? So this become our initial conditions, and we have found the first step. So the first step actually is to look at the circuits before switching, and then look at the continuity after switching, and that will set the initial conditions for our circuit problems. Okay, and from the analysis of the initial conditions, you can also see that actually we can also calculate the steady state values after switching, correct? Because after switching, your inductor will behave like a short circuit at steady state, right? Take note that this is steady state, must be steady state. And then capacitor will behave like an open circuit at steady state. Okay, this means that I can calculate this steady state current because this is just a resistor network, right? And because this is 0, right, as I said, the voltage across, these are all parallel. If the voltage across the inductor is 0, it forces the others to be 0, okay, including your resistor. If there's no voltage across the resistor, no current can flow through it. So all the current will flow through here, 3 ampere. That means that your steady state current is actually 3 amperes. Right? Steady state current will be equal to 3 amperes. Okay, we have found the initial values of the current. We found the steady state value of the current. Here you can see that the final value not necessarily must always be greater than your initial value, right? Not necessary. In this case, the analysis still apply. It just says that you start from 6, right? And then it's losing energy. Steady state is 3 amperes. Okay, but we do not know what is in between, right? But we know that there are 3 types of response. Either, okay, there are some oscillations, or there's no oscillations but slow, or critically damped, right? Reach there at the fastest possible time without oscillation. So 3 types of response, and this is what we're going to find out next, right? We know initial 6, final 3. How about in between? In between will depend on the values of your alpha and omega 0, which then will depend on your RLC values, right? So actually, in terms of circuit designs, you can design your RLC values to achieve different kind of response that you want. Okay, but here we only analyze it. So given the values of RLC, we check the values of alpha and omega 0. Right? So this is just substitutions. But if you forgot these equations, what you need to do is to try to derive the differential equations, right? And then this will be 2 alpha, this will be omega 0 square. From there, you can get these 2 equations, right? So as I said, you remember this, but if you cannot remember, then go back to basic Kirchhoff current law, derive the differential equation, then write down this as 2 alpha, write down this as omega 0 square. Then we can get the values of alpha and omega 0. Okay, which means that the remaining job is just to substitute. L is equal to 5, C is equal to 1 over 20, R is equal to 5. Right, put it into here, you can check that alpha is 2, omega 0 is 2.
Sorry, sir. I just want to double check. So the formula for alpha for the calculation of current IT and VT are different, is it?
Sorry?
The
They are the
formula
same
for
actually.
alpha, is it the same or different?
They are the same. They are the same. Actually, you can see that you can try to derive the voltage, because here actually I'm interested in here you're interested in current, right? If you want voltage, then you should get rid of I, correct?
Yep.
You should get rid of I. So I is what? I is this inductor. Okay, and then given I, you find voltage. How do you do that? Integrate, correct? Because this is equal to this. So in order to find I, okay, remember what you do is that this, right, is equal to V over L di dt. So by integrating this, right, remember you will have your initial voltage, okay, initial voltage, and your integrations of your voltage with respect to time. All right. After that, you differentiate one more time, you get actually a similar form. Okay, except the right hand side is different, of course. The right hand side will be different, but the rest basically are in a similar form. Right? You can go and try it out. So they are similar in that sense, but the steady state value will be different, because one is referring to the steady state values of the current, the other one is referring to the steady state values of your voltage. Right?
Okay. Thank you, sir.
Yeah, any question, you can just stop me, right? Okay, let's go back to where I stopped. Okay, so here, we're interested in current, so we just write down this in terms of current. If you're interested in voltage, you write it down in terms of voltage. Okay, and you can check that actually they are the same. Even source free, right? It's also the same. So by the way, source free, you just put this equal to 0, right? So I'll say that actually you can just remember the one with the source. Source free is a special case where there's no source over here, right? Equal to 0. And there must be initial storage. Okay, there must be initial storage. Otherwise, there won't be any energy, okay, given up to the circuits. Now, alpha is equal to omega 0. This is obtained by just substituting these numerical values, right? RLC values. Now, if you have a more complex circuits, then you must simplify to this form, right? Then that will be your equivalent RLC values. Okay, check it, and we know that alpha is equal to omega 0. Then we have this case, right? This case. So these are equal. Then you have equal roots. You have only one parameter alpha. I just put it here, and then, but there are two solutions actually, because this second order, right? So you can see that there are always two. 1, 2, 1, 2. This one also 1 and 2, but because they are equals, you put, there's one more t here, right? Okay, next is that we know that it is critically damped. Therefore, we pick these solutions, right? We pick these solutions, and this is what we know now. Alpha is equal to 2. Just put it into here, right? ISS was calculated as 3, right? ISS was calculated as 3, so it can be placed inside as well. Right? Just now I've gone through it. ISS was equal to 3. Okay, which means that our solutions, right, take this form. ISS plus these solutions. Next is to find the value of A1 and A2. So far what we have done is that we find the steady state value But you can see that this is called steady state because this will goes to 0. As t goes to infinity, this whole term disappears. Then you only have this value, right? And then the next thing is that we do not know A1 and A2 because A1 and A2 will depend on your initial conditions, right? Will depend on the initial conditions. Now, for this circuit, it starts from V0 equal to 0, I0 equal to 6 ampere. That means that we have obtained it from analyzing the circuits before switching, right, at steady state. And after switching, they will not change suddenly. It has to start from these values. Okay, there are two unknowns, A1 and A2. So basically, you need two equations, right? Two equations, which means that if you know the value of the current at any time, you can write down one equation for one value. Okay, let's look at it. We know the current at t equal to 0, correct? We know the current at t equal to 0 is equal to 6, so we can write down one equation. Okay, but the other initial condition is voltage. It's not the current, so therefore we need to relate to the current. So we leave it to this later on, which means that you start from this one first. It's easier because now you're considering current. So you relate to current. Like just now your classmate raised, how about voltage? If you consider voltage, then you start from the first initial condition. Put t equal to 0. Check the values of that. At t equal to 0, that must be equal to your initial condition. So if I put t equal to 0 into here, then I get here I0, that means I at t equal to 0 is equal to 3 plus A1 plus 0, this is equal to 0. E to the power of 0 is 1, right? You get 3 plus A1, and E must be equal to 6 ampere, right? Based on the initial condition. Okay, this means that 3 plus A1 is equal to 6, which means that A1 is equal to 3. Now actually, it simply means this, right? If you put 3 here, it simply means this. At t equals to 0, at t equal to 0, right, this term disappears. This is equal to 1. E to the power of 0 is 1. Then my current, I t equal to 0, must be equal to 3 plus 3, which is equal to 6, right? If you set this wrongly, then it will not be these initial values anymore. So this is the first step. Fix get one equations based on the first initial condition. Now it happened that in solving this, A2 disappear because A multiplied by t equal to 0. So we can solve it directly, right? A1 is equal to 3. Okay, next we have obtained A1 equal to 3. Let's solve A2. A2 can be obtained from the second initial condition, which is the voltage. Okay, take note that you have current. What is this current? Check your circuits. Current through the inductor, right? Current through the inductor is related to the voltage across it by L didt. Okay, this is what we have stressed, right, in one of the tutorials. Now, for inductor, the relationship between voltage and current is governed by this rule. Unlike Ohm's law, it's easy, right? V is equal to IR, multiply and divide by scalar. For this one, we involve integration differentiation. Okay, this means given I, right? Given I, find voltage. Okay? Find the voltage, then put t equal to 0. So I put V equal to del dt, which means that you have to differentiate this equation. Differentiate this equation with respect to time. Okay, of course, you have to remember how to differentiate this. I show it briefly over here. You can use product rules. You differentiate the exponential term first, you get this one. Right, fix this one. Okay, then next you fix the exponential term. You differentiate the terms in the bracket. Right? You get A2 only. Okay, because t differentiate with respect to t is 1. Constants differentiate with respect to time is 0. So this is my voltage across the inductor. Here you can also see that after you find this current, you can actually use it to find a lot of things, right? You can find the voltage across the inductor. Once you find the voltage across the inductors, it is also the voltage across the resistor, because they are all parallel. Then you can use Ohm's law to find the current through the resistor, right? V over R, which means this one divided by R is the current through the resistor. Now, to find this current, you have two choices. You notice that you already have this, correct? So you can use Kirchhoff's current law to find this, or you want to use the laws of this capacitor, right? Then you need to do integration. Okay, do integration because I is equal to C dV dt, right? I is equal to C dV dt. I is equal to C dV dt, so you differentiate the voltage. That means that you need to differentiate this one more time. Differentiate this one more time, multiply by Ci, because I is equal to C dV dt, right? But the easiest way is to use Kirchhoff current law, okay? Because you already, if you have found this, it's easy to find. And then this one, you have found it over here. This 3 ampere, right? So inflow equal to outflow, you can get this. Okay, let's go back to this initial condition. So we are in the process of finding A1 and A2. We have found A1. Now we are finding A2. Based on this initial conditions, V0 is equal to 0. But what we have is current, so we must differentiate it, relate to the voltage, right? Relate to the voltage. And the voltage across the inductor is also the voltage across the capacitor. Remember, this is the voltage across the capacitor, right? But they are parallel, so they are the same. So finally, I put T equal to 0. Then some of this term will disappear. This will be equal to 0. This will become 1, right? E to the power of 0 is 1. So basically, you get next equations and equate it to 0 because V0 must be equal to 0. Then we get A2 equal to 6. Okay, this means that A1 is equal to 3, A2 is equal to 6, and this gives us the solutions. And don't forget to put T greater than 0, right? Because this is after switching, right? Before switching, it was not in this form.
Sorry, so can you go back one slide? Yeah, sorry.
Sorry?
Sorry, just a moment. All right. Okay, thank you, sir.
Okay, so that's all for the last tutorials, and today we also will go into a new topic, Laplace transformation. Now, in fact, Laplace transformations, right, is a better way to solve differential equations. And what you have seen, right, the three forms of solution actually was derived from Laplace transformation. Okay? Laplace transformation, because the maths that are available for solving time domain differential equation problems are very limited. So a scientist, right, came up with this method called Laplace transformations. It's named after the persons, right, the scientist who invented it. Okay, the whole idea is to transform differential equations into algebraic norm differentiations and then solve the equations in Laplace domain and then take inverse Laplace transformation, right? So this is a key idea. Now, the notations for Laplace transformations is this. Now, firstly, if you have a signal in time domain ft, after transforming into Laplace domain, right, usually we put capital F just to differentiate from the time domain functions, and then the domain is S domain. Right, the domain is S domain, it's a functions of S. Now, this notation also means Laplace transformations, Laplace L, right? Laplace L, after transforming it, you get Fs, functions of S. Okay, and what is Laplace transformation is defined by these equations over here. Okay, that means that this mathematicians, he found this way of transforming a signals in time domain into Laplace domain by integrating the signal in time domain, multiplying it by e to the power of negative st, right, and then integrate respect to time from 0 to infinity. So Laplace start from 0, right, start from 0 only for positive axis. right? So remember that. And then this S is actually a complex variable which consists of a real part and an imaginary part. Right? So Laplace domain is also a complex plane. Okay, and in your notes, basically you have there are a few examples. Okay, these are some standard signals which are commonly available or commonly used. For example, UT actually means a unit step function, unit, right? Step functions, unit means 1. Step means that you change it suddenly from 0 to 1 at t equal to 0. Right? Actually, UT, right, in Laplace, it just means that it's equal to 1. Why? Because Laplace starts from 0, right? Start from 0, so after 0 is always equal to 1. Therefore, this is actually equal to 1 for unit step function. So you put 1 here, and then you integrate it. If you integrate e to the power of negative st, right, it's 1 over s negative e to the power of negative st. Put the values from 0 to infinity, right? Then if you put s equal to infinity here, it disappears. You put s equal to 0, right, and then 0 minus negative, you can positive 1 over s. This basically means that the Laplace transformation of a constant of 1, right, for t greater than 0 is equal to 1 over s. Now, fortunately, you need not remember this, okay, but you use a table, right, to refer to this. Okay, let's go through one more examples. E to the power of negative st, e to the power of negative at, right, is what you want to analyze. Now this ut, right, it just means it's equal to 1 because we're considering t greater than 0. T greater than 0, u is equal to 1, which means that you have this signal, right? You have this signal exponentially decreasing. Okay, before that, right, it was equal to 0. Now you put these signals into here. This is what we get. Then you get these terms, and integrating this term, right, you put this to the front. Impose these conditions, t equal to infinity, t equal to O, 0, you get 1 over s plus a. So this just means that the Laplace transformation of this exponential term in time domain is equal to 1 over s plus a in Laplace domain. Okay, as I said, you do not need to derive this, fortunately. Right, for this course, we focus on how to use this table. Now, just now I've shown it to you. Right, somebody has done this already. Laplace transformations of ut is 1 over s. Laplace transformations of exponential term is 1 over s plus a. So they have done a lot of other commonly available signals, commonly used signals, and put it into a table. Okay, here we only need to use it, right? Know how to use it, but you should know that it was derived by these basic formulas, basic definitions of the Laplace transformation. And all here, there it includes DC signals. Step is DC, constants after t greater than 0. You also include AC, right, sine and cosine. So include a broad range of signals in this circuit. Some of them you may not use it, right, for this course, but this is the complete one. And as I said, these tables, right, will be available. No need to memorize it. This is what I straight out from the exam papers. Right, in the exams, you also will be provided with these tables. And some of these terms, right, if you look at it carefully, it actually related to what we have done just now. This is the underdamped response, correct? A combination of these two. So you put A1 this, A plus A2 this, you get an underdamped response. So actually from the table, you can kind of remind yourself, right, what will be the terms to be used in the three form of solution in time domain. Okay, and then for the overdamped is actually two values of alpha 1, alpha 2. So you have two of this, right? A1 e to the power of negative 1 alpha 1 t plus A2 e to the power of negative alpha 2 t. So you use two of this term because alpha are distinct. Now, if you have repeated, then one of them will be this, right? One of them will be this, the other one will be here. The other one will be here. So basically, these four terms, Okay, the last two for under them, these two, right? The first one for over them, and the combinations of these two is for critically damped. Right? Actually, it means that you can get all these terms here. You need not remember much actually. Now, this property is very important, and actually, a lot of you have used it without realizing that you're using it. It says that if you have a constant multiplied by a signals, then the Laplace transformations of a constant multiplied by signal is just the constant multiplied by the Laplace transformations of the signal, right? If you have linear combinations of such similar ones, A2, F2, right, then you just add it up similarly. Now this is useful because if I have a linear combinations of two signals, right, then I can just take the Laplace transformations of them individually and add them out in the linear combination as well. So the whole idea is that you can take A constant out of the Laplace transformation, right? And then you take Laplace transformations of the remaining one, you get this A1 F1 plus A2 F2. Okay, the other most important property is actually time differentiation. Okay, I'll go through this proof, but actually you need not remember it. Just understand how, right, this is derived. That means that I'm trying to derive this. Okay, but this, as I said, will be available in the table, right? In the tables, you can just use this property. Now, here, take note that if I want to take the Laplace transformations of a signals, f is fs, right? But if I want to take the Laplace transformations of differentiation of these signals, it is actually fs minus the initial condition. This is important because it means that to find the Laplace transformations of the differentiation of the signal, you need not differentiate the signal in time domain, right? No need differentiate the signal in time domain. You just take the Laplace transformation of the signal without differentiation, multiply by s. So next time if you see sfs, right, it means differentiation in time domain, right? Fs in Laplace domain, implying that there's a differentiation in Laplace domain. Okay, the other one is integrations. Right, integration is just divided by s. Fs divided by s is integration. Fs multiplied by s is differentiation. Right? Now this one integration we hardly use, but just to let you compare them, right, as a reference, Fs multiplied by s differentiation, Fs divided by s integration. Now here, right, this property, okay, we will not need to remember it, okay, but you must know how to use it, right? This basically means that if I want to take the Laplace transformations of a differentiation of a signal, then I just find the Laplace transformations of the signal without differentiation, which is Fs, and multiply by s, then I minus the initial conditions. I'll get the Laplace transformations of the differentiation of the signals, right? So I need not differentiate it. Okay, here I'll show how we can prove it, right? That means that how this is equal to this. Remember, the basic definitions of Laplace transformation is that you're integrating the signal by multiplying by e minus e to the power negative st from 0 to infinity, all right? Now, notice that there are two terms here. Now, if I want to take the Laplace transformations of the differentiation, I should replace, right, just replace this signal by df dt. This is the basic definition of Laplace transformations. I multiply df dt by this, and I integrate from 0 to infinity. Okay, and here I need to integrate two terms. Then you should review your integration by parts. Now, integration by part work this way. Find one of these terms. There are two terms here. Find one of them which can be integrated, right? Then you put into both terms. That one that can be integrated. Okay, the other terms, one of them you put it as it is into this term. The other one you differentiate it. Du prime means differentiation, and put it into the other side. Now here there's the integration. There's no integration here. Then there's a negative sign here. All right, so this is the integration by part. Okay, I'll switch this order around because df dt can be integrated into f, right? df dt integrate is f. Go back. Differentiation, integrate it, you get back f. Okay, which means that my integrations of this, integration of it can be put into here. So this is this one, right? Integrations put into two parts. Okay, the other one I put it directly here, one I differentiate. Right? One I put it directly here, one I differentiate. Okay, which is this one. In differentiating this, you get negative s, but there's a negative sign here, so you get positive. Negative, negative will become positive. Okay, then you impose these conditions. You can check that, right? E to the power of negative infinity is 0, and minus the initial conditions. E to the power of 0 is 1, f0 is the initial values of f. This s term can be taken out because this integrating with respect to t. Then the remaining term, look at it, is your fs, right? It's your fs, so this is s, fs minus the initial condition. So I'm deriving this. Go through it once, right? Convince yourself that this is true. Then after that, we'll use the table. Okay, again, these tables will be available during exam. So if you want to find differentiations of a signals in Laplace domain, then this is what you do, SFS minus the initial condition. Okay, with this we can now solve problem 1. Okay, here if you see this one, you have a signal in time domain. You want to find the Laplace transformation of the differentiation of the signal. So you have two choices. First, you're going to differentiate it in time domain, then take Laplace transformation, right? But if you know how to use this property, then you need not differentiate it at all, correct? So this is easier. I do not need to differentiate it, rather I use this property. We say is that I only need to find the Laplace transformations of the original signals without differentiations. Then you put into here, multiply by s minus the initial condition, right? So this is a key idea. Fs is the Laplace transformations of ft. Then how do we find the Laplace transformations of this ft? Go to the table, right? Go to the tables. So determine fs from the tables, and we need to also find the initial condition if it's not given. Let's go to the tables. This terms, e exponential term with a cosine, is actually the last one. Exponential term with a cosine, right? So I put this term here for ease of reference. My a is actually equal to 4. Okay? My omega is actually equal to 2. So put a equal to 4, omega equal to 2. Then you get this term. Now be careful, there's a 2 here. Alright? There's a 2 here. So this is a kind of linearity property. Okay? To take Laplace transformation of this, you can take the 2 out of your equation, correct? And then you just multiply by 2. Okay, which means that the Laplace transformations of 2 times of this is actually 2 multiplied by Laplace transformations of these signals. And we get Fs, right? So Fs has been obtained. We still need the initial conditions, which is not given, but the initial condition is just the value of this function when t equal to 0, right? Just put t equal to 0, e to the power 0, 1, cosine 0, 1, so it's equal to 2. Okay, we have obtained these initial conditions. Now we use this property, right? Put this into here, which means multiply by s, and put 2 into here. I can get my Laplace transformations of the differentiation of the signal, okay, without differentiating the signal. So this is a key idea, right? In Laplace domain, differentiation disappears. We do not need to differentiate anything. Okay, after this, you can try to combine these two terms together, and then if you can simplify it, as in this case, some terms somehow cancel out, right? 2s squared minus 2s squared, no more. 8s minus 16s give you negative 8s, right? And then finally, you have negative 2 times 20, which is negative 40. Okay, we have seen how to take the Laplace transformations of the differentiations of a signal once. Now, how about d square f dt square, right? Remember, we have second order circuits as well. So you need to know how to take the Laplace transformations of a higher order term. Now, this is how it works. Right? Actually, you can see that d square f dt square is just to differentiate df dt one more time. Correct? Differentiate df dt one more time. And we have know how to take the Laplace transformations of one differentiations, okay, which is S. Laplace transformations of your df dt now, minus the initial condition of df dt. It means df dt now become your signals. You apply this formula, this become your df dt. Substitute by df dt, you get this one. Okay, now this one, Laplace transformations of df dt, then do one more time. Using this formula, do one more time, you get S. Fs minus the initial conditions of f. The first one was the initial conditions of df dt. Second one become the initial conditions of f. So you get this one over here, right? Which need the initial condition of f and its differentiation. Okay, fortunately, this you need not remember. It can be obtained from the table, but the table gives you a more general one. Okay, which is obtained by induction. That means that this give you this. If you keep doing this, right, by inductions, you can get this general one. Okay, I'll just go through how you use this general one, which is available in your table as well. Right, whether is it lecture notes or exam, this table will be available. Right, for if you did d square f dt square, you put n equal to 2. Right, just put n equal to 2 into here. Right, until this becomes 0. N equal to 2, this will become s to power 0. N equal to 2, this will become s to power 1. N equal to 2, this s square is exactly this one. Right? And the rest, no more, because you reach 0 already. So put s equal to 3. Similarly, you can take the differentiations of d cubed f dt cubed. So the nice thing about Laplace transformation is it's not limited to second order. It can be used to solve higher order differential equation as well. So basically, you need to use this tree, right? The rest, right, is not that frequently used in this course, but you will use in your senior years in other courses. Okay, let us move on. Now, in the earlier weeks, we have seen how to solve a first order source-free circuits, correct? It means that you basically integrating this equation, you get a solution. Okay, actually this can be solved in Laplace domain by using these two properties. Linearity property, right? These are linear combinations of two terms. Right, this involves differentiations, so we need to use this property. So if you take Laplace transformations, then dV/dt you get SVS minus initial voltage. Using linearity property, right, the second term plus 1 over RC, a constant, multiplied by VT will become constant multiplied by VS. Now look at these equations. There's no more differentiations. That means that after imposing your initial conditions, you can do algebraic manipulation, right? Okay, namely, here you can see that you can take out Vs. Then I'll have S plus 1 over RC Vs. Okay, the initial condition, I move it to the other side of the equation. Okay, that means those terms relating to your solution Vs, group them together. Those terms not relating to Vs, put it on the other side. Okay, then this will basically give you the solution in Laplace domain. Okay, this is a solution in Laplace domain because we transform the differential equation from time domain into algebraic equations in Laplace domain. Then since there's no differentiation, we can just do algebraic manipulation, correct? And then you get a solution in Laplace domain and take inverse Laplace transformation. Okay, look at this term is 1 over s plus a multiplied by constant v0, correct? So we use 1 over s plus a. 1 over s plus a is 1 over rc. So therefore you get e to the power of negative 1 over rct in time domain. And this is linearity property. Right? This term multiplied by a constant, okay, will be equal to the constant multiplied by the signals in time domain. So you can get these solutions, right, through this Laplace transformation. So the general concept, right, in your notes is that you have a differential equation, include integration as well. Right? Integration can be done, but here we focus on differential equation. We can take Laplace transformations to get algebraic equations in Laplace domain. Right? Impose the initial conditions. Then we do algebraic manipulations. We get the solutions or revised equations in Laplace domain. Then take inverse Laplace transformation. You can get back your solution in time domain. Right? So this is a key idea. So let's look at question 5.2. Now this, you can treat it as this part, right? It means that assuming we have done all this, we get some solution. Then we want to take the inverse Laplace transformation to get back the solution in time domain. Okay, but however, after this algebraic manipulation, especially for higher order differential equation, right, you'll find that you cannot take inverse Laplace transformation directly. Because if you search through the table, you cannot find any terms like this or this, correct? We can't find any of this term which is directly in this form. But remember your linearity property. Okay, the key idea is that try to express this term as linear combinations of those terms that can be found in the table. Right? Which means that if the term cannot be found in this table, try to express as linear combinations of this term that can be found in the table. For example, by partial fractions, I can put this into linear combinations of 3 terms. Okay, which is linear combinations of these 3 terms with different a, right? With different a, this a equal to 1, a equal to 2, a equal to 3. Then I can take inverse Laplace transformations, right, to get the solution. And of course, you need to know how to take partial fractions, right? So partial fractions is asked to express this original function into a linear combinations of 3 first order fractions that can be found in the table. Then you can take Laplace transformations by using the linearity property and the table, right? So I'll start with finding A. Now look at this equation, the top one first. There are 3 unknowns. There are 3 unknowns, A1, A, B, C. Now 3 unknown, you need 3 equations, correct? You need 3 equations. Technically, left hand side must always be equal to right hand side, regardless the value of S. That means you can substitute any value for S to get one equation. For example, if I put S equal to 0, I get one equation. I put S equal to 2, I get another equation. I put S equal to 3, I get another equation. So if you have a powerful calculators, right, you can just substitute 3 values of S into these equations, and then use the calculator, you can get ABC, right? But that is not the most effective way to solve it, because a more effective way is to find A, B, C separately, and it can be done. Okay, how this is done is that if I multiply both sides of the equation by s plus 1, okay, the key idea is that I want to cancel out this term. Right? Because when you're multiplying together, then they will cancel each other, and then you get A, right? You get A. So that I can substitute s equal to -1 into it. Okay? When you substitute s equal to -1 into here, you get problem because you're dividing by 0, right? You can't do that. You multiply by s plus 1, then this term disappears. Okay, the nice thing is that this term and this term, after you put s equal to -1, they become 0, right? They become 0. So you only end up with A. So A is the value of this. This also cancels out. So A is the value of this term when s is equal to -1. And you can check that it's actually equal to -5 in the end. So this is actually your so-called cover-up rules. Right? Given these terms, you remove this term, put the value of s equal to -1. Then you get A. I'm just trying to show you, right, what is the meaning of that. Right? It's actually to substitute s equal to -1 after multiplying both sides by s plus 1. The key idea is that I only want A. So A is -5, which means that you get this term now. Now, if you understand this concept, then you know that to find, right, to find B is to multiply both sides by s plus 2. So that you only have B, then A and C will disappear. After you substitute s equal to -2, right, then these terms, right, will be cancelled out also because you multiply by s plus 2 and you only have this term. Put s equal to -2, you can get B directly. Lastly, to find C, multiply by s plus 3, put s equal to -3, you can get C equal to -15. Okay, in other words, I'm just trying to show you the partial fractions. By partial fractions, I can put this term as a linear combination of 3 terms, and all these terms can be found in your table, right? S plus A with A equal to 1, 2, and 3. This means that you have exponential term with A equal to 1, 2, and 3. A equal to 1, A equal to 2, A equal to 3, linearity property. You get a linear combinations multiplied by -5 plus 20 and -15, right? And don't forget to put t greater than 0 or multiply by ut. So I hope everybody get the ideas for the solutions which you cannot get from the table directly, and factorize them into a linear combinations of the factors that you can get from the table, and then use linearity property to take inverse Laplace transformation. Okay, next we have this solutions. Okay, and also we cannot find in the tables. Okay, firstly, you have to try to factorize this, right? S squared plus 2s plus 5. Now, if you can factorize it, right, then you go back to here, right? You go back to here. Okay, but some cannot be factorized. Okay, this one, if you try to factorize it, you can't factorize it into real factors, right? It will be imaginary solutions. Okay, in this case, you should do it this way. Okay, this is s squared plus 2s, right, plus 5. I plus 1, and then I minus 1, right? It still remain the same. Now, why I plus 1 is because here I can put them into s plus 1 squared, right? And then over here is plus 4, plus 4. So essentially it becomes this s plus 1 squared plus 2 squared. Okay, it cannot be factorized into two real factors, but it can be put into this form. Okay, if you look at this one, you can see that it's always positive. Okay, that actually means that you cannot find a real solution. Right? In fact, you are more familiar with this, x squared plus 2x plus 5, right? It's actually the same. It's just that here we use s. Suppose that you have y equal to this. Okay, when you plot it out, it's a polynomial. All right, and if this term, it just means that your y is always positive. It can never be negative. It can't even be 0. Okay, which means that it cannot cross over 0. Right? It cannot cross over 0 with real solution. Okay, with the real solution. The solution will be imaginary. Since this cannot be factorized into first order factors, we let it remain as second order, right? Let it remain, which means that your partial fractions will be a linear combinations of the first order factors and the second order fraction, right? And the numerator is always one order less. If you have s, right, then will be constant. If you have s squared, then will be s to the power 1, right, plus constant, right? It's always one order less. So we have three unknowns, a, b, c. Now a can be found by similarly multiply by s plus 2. Right? If you multiply by s plus 2, put s equal to -2, then this term disappear. No more b and c, which means that you only have this term. S plus 2 cancel out. Put s equal to -2, you can get a. Okay, but the second terms, b and c, you can't do that anymore, right? Because you can't make this equal to 0. You can't multiply by this and make this equal to 0 anymore. But it's okay because we have found a, right? We have found a, -1/5, so this is known. Okay, which means that there's only two unknown. There are only two unknown. Okay, two unknown, you just need to put two values into this equation. And then you solve two equations with two unknown, right? Which is quite easy to solve, right? So actually solving two unknowns is to establish two equations and then solve it. For example, just substitute any value of s into it, you get one equation. Substitute another value of s, you get another equation. Then you solve for it. Okay, but there's always a better choice. Right? A better choice is obtained by substituting s equal to 0. Right? It does not cause any division problem by not dividing by 0. And s equal to 0 is easy to evaluate. Left hand side, s plus 1 become 1, s plus 2 become 2, s squared plus 2s plus 5 become 5, s equal to 0. And right hand side, right, this becomes 0, you divide by 2 only. B map out by 0, you have only c, right? And then dividing by 5, because the rest will be equal to 0, you can solve this easily for c is equal to 1. So c is equal to 1, and the only unknown is b, but now you can easily solve this because there's only one unknown. Put any value of s. 1 is good because 1 is usually easy to calculate, right? So put s equal to 1 into both left hand side and right hand side, and then you can solve for b, which is 1/5. So b is now known, which means that I have factorized, right? Factorize this partial fraction, expand into two factors, two fractions, linear combinations. Okay, next is to remember that my s squared plus 2s plus 5 can be put into this form. All right. Then I try to find this from the table. See whether you can find anything in this table. So why this is put into this form is because, right, you can see the last two terms is in a similar form. S plus a squared plus omega squared, right? S plus a bracket square plus omega squared. But in order to use this, right, you must have exactly in this form. That means that the closer one is the last one, s plus a. But you go back, this is not s plus a. This is 1/5 s plus 1, right? It's not s plus a. Okay, therefore, what we can do is to try to express as a linear combination of these two terms. Okay, linear combinations of these two terms. Now, how do we do that? Okay, first is to take note that 1 over 5s, correct? I try to get this s plus 1 because a is equal to 1. A is equal to 1, I must get s plus 1. This is 1 over 5s plus 1. It's not s plus 1. But to get s plus 1, you just add this and minus this. Correct? Just add this and minus this. Add 1 over 5 minus 1 over 5. So I get something like that. S plus 1, s plus 1, which is exactly in this form. Right? So I settle the first term. Now, the second term is 4 over 5. Now you check the second term. Not exactly, this must be equal to 2. Right? 2 square, a is equal to 1. This must be equal to 2, but 2 is easy, correct? 2 is just 2 over 5 times 2. Right? That means you take out 2 from this. You get 2 over 5. So 2 over 5 times 2. Right? 2 over 5 times 2. Okay, then basically I get a linear combinations of these two. Right? One is this first term, the other one is the second term. And 1 over 5, right, is 0.2. 2 over 5 is 0.4. So I can take inverse Laplace transformations, okay, to get a linear combinations of these two terms. And for the first order factors, right, is the exponential terms. 1 over s plus 2 is e to the power of negative 2t. 0.2, right, is 1 over 5 negative sign. Any questions? So if you go back to read your notes again, right, this is how you should do in your learning. Read through it once, don't understand, all right, never mind, do some problems, solve it, some examples, solve the tutorial problems, go back, read again. Now this makes more sense, right? You have these solutions, which is the fractions. You decompose it into a linear combinations of those terms that you can find in the Laplace transformation table, so as to use the linearity property to find the inverse Laplace transformation. Okay? So any general solution which you cannot find in your table, decompose them by partial fractions into a linear combination which match your entry in the table, and then make use of the linearity property to find the inverse Laplace transformation. Right, there's also this note saying that the order of your numerator must be less than the order of your denominator, as in this two, right? This is first order, this third order less than. This first order, this third order is less than. But there will be some cases where it is greater than or equal to. For example, this is second order, this is also second order. Then what you need to do is just to expand it further by division. Okay, because this can be expanded into these two parts. Then you have a linear combination again, right? One you just find from your Laplace transformation table is an impulse, and the rest is the same. Expand it out by partial fractions. Right? Once the order is less, you can expand by the partial fractions. Then you get more terms, and you can get linear combinations of them. Right, so order more, you get something else, right, which you can also expand as linear combination, find the inverse Laplace transformations from the table and expand the rest by partial fractions. We can also get the solution. Any questions before we move on to the last problem? Now for the last problem, remember, right, circuit laws still apply. So basically, given a circuit, if you have write down the equation in time domain, right? Maybe Kirchhoff current law, just now I show you, write down equations. You get this differential equation now, and you have found the initial conditions. Okay, this means dt at t equal to 0, right? The values of the differentiations of v at t equal to 0. Okay, the notation is also v prime 0 is equal to 4. Now here we have a problem in solving this differential equation. This is not dc, it's exponential term. So you cannot solve it anymore. You have to use Laplace transformation. Okay, Laplace transformation is nice because it's not limited to DC, right? What we have learned last week is only limited to DC. This can be used for any signals, right? So long as you can find in the Laplace transformation table. Okay, let's look at these problems. I should now make use of the differentiation property. Okay, in particular, second order, I use n equal to 2. Then I can take the Laplace transformations, right, of this differential equation by using the properties of time differentiation. dv dt, let's start with this one, will be transformed into SVS minus V0. No need to remember, just get from the table, right? Get from the table this one. Okay, for n equal to 2, if you use that table, n equal to 2, put n equal to 2 into this one, right? You can also get these equations. S squared Vs minus SV0 minus V prime. V prime is what? V prime is your initial conditions given, right? This one. This V0, this V prime. Okay, which means that we actually have this one, and this one, all given to you. Okay, then by putting this into here and putting this into here, we transform, right, the differentiations of v respect to time 2 times into this. The linearity property plus phi dv dt plus phi SVS minus initial condition, linearity property plus 6v plus 6vs equal to, now don't get confused by this one, right? Just put equal to 1. Because Laplace transformation is t greater than 0. Ut is equal to 1 for t greater than 0. Right? Then it's just this exponential term. Check the table. E to the power of negative 1t is 1 over s plus 1 in Laplace domain. Multiplied by 6. Okay, look at this equation. There's no more differentiation now. It becomes, we call algebraic equation, right? Where I will group all the Vs, the solution, together. Right? Then you get s squared plus 5s plus 6 bracket Vs. Okay, the remaining term, put it to the other side of the equation. Right? Put it to the other side of the equations, though without Vs. Then you can get us solutions by dividing by this. Right? Dividing by this. And s squared plus 5s plus 6, fortunately, can be factorized into real terms. Right? If you factorize it, you can check that it's s plus 2, s plus 3. Okay, which means that I replace, right? I replace it by this. S plus 1, no need to do anything, right? It's already a first order fraction, first order factors. Okay, then I know that this is my solution in Laplace domain. I should express it as linear combinations of 3 terms that can be found in the table, right? Which is 1 over s plus 1, 1 over s plus 2, 1 over s plus 3. Okay, the rest is partial fractions. I will not go into that anymore. Right? You can multiply by s plus 1, get this term. By substituting s equal to negative 1, or you use cover-up rules directly, right? And then you can find this term and this terms, and you can see that inverse Laplace transformation, you get this multiplied by 3. Linearity property for e to the power of negative 2t. Same thing, negative 5t, linearity property, e to the power of negative 3t, right? Don't forget to put t greater than 0 or put a ut there. It means the same thing. So I hope everybody get the ideas. Right? If you have formulated a differential equation in time domain based on circuit analysis, then we cannot solve it in time domains. We transform it into Laplace domains by using this property, right? Differentiation property, and we impose the initial conditions. Then this is algebraic equations. We can do algebraic manipulations to find the solutions in Laplace domain, and we expand it out by partial fractions into 3 first-order fractions so that we can take the inverse Laplace transformations by using the table, right? Because this is a linear combinations of 3 first-order fractions. By using linearity property, we can find the solutions in time domain. And notice here is that, right, this term here, okay, actually is because of your input, right? You have an input. Sometimes we call force input. Right? You want to force the circuits to follow this input. Now, if you put a DC here, your force response will be DC. You'll see a DC here. If you put an exponential term here, you're forcing the circuits, right, to have this kind of response. Okay, if you put AC here, you will see an AC output, right? Force response, force input, force response. Okay, the other two are the natural response. Right? The other two are relating to your natural response. Okay, because Y is relating to this term. Okay, in fact, you go back to this equation, you see that, right, my differential equations 5, 6, correct? 5 and 6 will appear here. 5 and 6, the system's characteristic natural response, and then you factorize into 2 and 3, right? As a result, you get these 2 and 3, and finally, you get this response, 2 and 3, you get this 2 response, e to the power negative 2t, negative 3t. So this will always be in your circuits, natural response, right? This one will depend on your source. Okay? If your source put in this exponential term, then you get this one. If you put DC, this will be DC. You put AC, this will become AC, but the other two will always be the same, right? In fact, you can go back and try, put this as a DC, right? Put this as a DC, then go through Laplace transformation, you get a DC output here. So this is your force input. This is your force response. Right? This is because of the natural response, 0. Okay, it will give you this one. Any questions? Okay, for the summary right at the beginning of this tutorial, right? I will post it in the course website. Right, later on, I'm still trying to prepare it. I'll post it in the course website, right, so that you can refer to it. Okay, that's all for the tutorials. Any questions? Okay, if not, thank you. I'll see you next week.
Thank you, sir.
Thank you. Bye.